Hello, my name is Colin Drews. I'm presenting our work Classifying Computations on Multi-Tenant FPGAs, which is a collaborative effort between myself, Mustafa Gobuluku, and Professor Ryan Kastner from the University of California, San Diego, as well as Bill Hunter of the Georgia Tech Research Institute and Dr. Dustin Richmond of the University of Washington. FPGAs have emerged as an ideal tool for offloading compute-intensive operations, like genomic sequencing, networking, and encryption in data centers. The current offerings in cloud environments to utilize this acceleration employ an all-or-nothing approach, requiring renting an entire FPGA regardless of intended application. Abstracting the FPGA's resources through virtualization to allow users to pay for as much as they use has been proposed to increase utilization of these devices. However, virtualization introduces a new class of security problems, as multiple users within an FPGA may share the same power distribution network. A recent class of side-channel attacks, which implement a voltage fluctuation sensor within the programmable logic of the FPGA, have been used to attack logically isolated computations which share the power distribution network. In this presentation, we will introduce the ability to classify the type of co-located computation in a virtualized FPGA environment using a voltage fluctuation sensor. We extract the type of computation, for example, whether the user is running AES encryption, as well as the implementation of that algorithm. Is the computation running on a soft processor? If so, what one? Or is it implemented as an HLS core? Such an attack serves as an important precursor for existing side-channel attacks. For example, a DPA attack relies on the knowledge of the existence of a cryptographic core. We present the following attack scenario, where a remote attacker aims to use a voltage fluctuation sensor to classify a co-located application in a data center's multi-tenant FPGA. The attacker first packages the voltage fluctuation sensor, the design of which I'll discuss in a moment, and uploads the design to the user's allocated region of the remote FPGA. A set of sensor readings are then captured remotely, and the attacker transfers them back for local analysis to be classified based on the computation that was present on the FPGA when the sensor was sampled. We assume that the attacker has access to a set of IP cores which are representative of what may be encountered in the multi-tenant FPGA environment, thus allowing the attacker to have executed these computations alongside the sensor in a controlled environment for building a corpus of labeled training data for each computation. The sensor employed in this attack is a time-to-digital converter, which senses variations in the power distribution network. The speed with which transitions propagate through a linear array of delay elements is a function of these variations. To extract a reading from the sensor, the value of these delay elements are captured at a particular point in time. When captured periodically, we are left with a power trace over time, which is representative of the state of the power distribution network. Power traces captured by a remote attacker are then processed as follows. The raw binary sequence outputted by the sensor is transformed through a population count, or simply the number of ones in a binary trace, to get a 1D signal. A short-term Fourier transform is applied over windows of this process trace to encode the frequency domain of the signal at a given time. Finally, ResNet50, a convolutional neural network which has been trained on labeled traces captured locally in a controlled environment by the attacker, is used to derive a class from a newly captured trace from the remote environment. To study this classification, we examine 9 unique computations. We deploy baseline, the absence of any computation, power wasters, a malicious circuit implemented with banks of ring oscillators designed to aggressively consume power. Finally, 2 encryption algorithms, AES and PRESENT cipher, are implemented on 3 soft processors, ORCA, PicoRV, and Microblaze, as well as a custom IP core running AES. When an attacker captures a trace that it wishes to classify as one of these computations, our 3-stage classification pipeline is applied as follows. First, 2D trace output from the sensor is converted into a 1D output through the population count, which again just counts the number of ones that appear in a given sample. The population count is a function of the propagation of a transition within the sensor's delay elements, and as a result, its value in some way reflects the state of the power distribution network. Next, a Fourier transform is applied to windows of that 1D signal to generate an image encoding the frequencies present in the trace over time, which is unique to some aspect of the co-tenant computation. In this example here, we show the image encoding of the ORCA soft processor running the AES block cipher. Finally, those images are fed into the ResNet50 classifier, which extracts a label from the given image. This classifier has been trained on a set of images which were generated locally by the attacker in a controlled environment using the representative IP cores. We then test the network on a reserved set of images which represent traces captured in the remote FPGA environment in the attack scenario. We train and test the classifier on different sizes of traces to determine the length of sensor sampling needed to accurately determine the type of co-located computation. While using the whole trace length performs the best, a 91% classification accuracy, because the 9 computations take a different number of clock cycles to complete, and by encoding these variable lengths in a fixed-sized image, we may potentially introduce bias, we focus on the shortest segment length, which does not have this property. The shortest runtime of any application is 16,000 sample traces, where a sample is a single pop count value. So we set this as the longest length of trace we will classify. Traces of applications that are longer are segmented randomly into 16,000 sample blocks. As a result, all STFT images encode an equivalent amount of sensor output. With this mitigation, we still find that classification is very strong, nearly a 70% accuracy in distinguishing between applications. We perform the same process, except on smaller segments of traces to determine the amount of time a sensor needs to sample to capture identifiable information about a co-tenant. Classification accuracy improves the longer the sensor samples, strictly increasing as the number of samples is iteratively doubled, starting from 35% accuracy with only 64 samples up to 70% accuracy with 16,000 samples. Notably, we find it is possible to determine the type of co-located application 3 times better than random inference with samples of only 32 cycles, which is less than 0.2% of the execution time of the shortest application and 0.0064% of the execution time of the longest. In our 9-way classification, we identify trends in the misclassification of applications, distinguishing between architectural implementations, HLS, AES, ORCA, Microblaze soft processors, is very strong. In contrast, extracting the algorithm running on a given implementation is challenging, evidenced by the misclassification between AES and PRESENT cipher running on each one of the soft processors. In this presentation, we have offered a pipeline for remotely classifying the computation of another user in a multi-tenant FPGA environment. An attacker utilizes a time-to-digital converter to locally capture representative traces for a set of applications. These labeled traces are then used to train a classifier, at which point an attacker can upload the sensor to a remote FPGA environment to capture a trace which we wish to extract the type of co-located computation from. Our 3-stage classification pipeline takes this trace, converts it into a 1D signal, applies the STFT transformation to get the encoded frequency information over time, then is finally inputted to our trained classifier, which outputs the computation the trace captured. We study this classification pipeline in a hypothetical multi-tenant environment where we implement 9 applications in logical isolation to our time-to-digital converter. A set of traces are generated for each application and used to train the classifier with a reserved set of traces which undergo the 3-stage classifier pipeline. This is able to confidently distinguish between computations with a 70% accuracy. The strong ability to classify between co-located computations presented here serves as a valuable precursor to traditional multi-tenant side channel attacks, which are often reliant on the knowledge of the presence of a particular co-tenant computation. Thank you.